Hey guys, welcome to eMaths and let's do some maths for fun. I think for most of us, we hated calculus so much during high school. So today, I will be making my first video on Fundamental Differentiation Formula. What I want to do is, I want to prove all of them. No kidding, 18 of them. Because I really wonder, where did they come from? We will start with the very basic rules, which are the first principle, constant rule, power rule, constant multiple rule, sum and differences rule, chain rule, product rule, and quotient rule. But before that, we have to first understand the concept of differentiation or derivative itself. It actually came from the tangent line problem. Consider we have a graph of function fx, and we have a point of coordinate x1, y1. We want to find the tangent line at point P. And the problem of finding tangent line at point P boils down to find the gradient or slope of tangent line at point P. For this problem, we need to understand two important concepts. Number one is the gradient or slope that we learned in coordinate geometry, and is defined as y2 minus y1 over x2 minus x1. The second concept is the secant line. In this case, it is just a line that passes through 2 points on the same function curve. To draw a secant line on this graph of fx, we just have to plot another point of Q with coordinate x2, y2. From point P to Q, we just connect it and we call it, this will be our secant line for the graph fx. We will label the change in x as delta x and the change in y from P to Q as delta y. We substitute into the gradient formula. We will have the gradient m equal to delta y over delta x. The beauty of this secant line is we can obtain more and more accurate approximation to the gradient of the tangent line by choosing the points closer and closer to the point of tangent C. For example, in this animation, you can see this point is what we want to find the tangent line, and we call it the point of tangent C. And the moving point is the point that we choose to draw the secant line, and you can see that as it is closer and closer to the point of tangent C, eventually our secant line will become a tangent line. As x2 approach x1, we can say that delta x, which is equal to x2 minus x1, approach 0. Hence, it will become the limit of x2 approach x1 of the gradient y2 minus y1 over x2 minus x1 will equal to m. And we can write limit of delta x approach 0 of delta y, which is a change in y, over delta x, which is a change in x, equal to m. Thus, d dx of y will be equal to the limit of delta x approach 0 of delta y over delta x. This is the first principle of differentiation. The derivative of a function, the concept is defined as f prime x, which is the derivative of fx, is equal to the limit of delta x approach 0 of f of x plus delta x minus f of x over x plus delta x minus x. If we simplify this, x can cancel out each other, then we'll have limit of delta x approach 0, f of x plus delta x minus f of x over delta x. This is what we define as differentiation. There are several common notation of derivative that we will commonly use. Number one is f prime x. Number two is d dx, then bracket fx. We will read this as derivative of fx. The third one is y prime. The fourth one is d dx bracket y, which is also written as dy dx. And we will read this as derivative of y respect to x. And the last one is capital D subscript x, and we bracket y. These are all the common notation that we will use for derivative. Okay, now we will proceed with the proving of that fundamental formula. The second rule, which is the constant rule. Consider a function of fx equal to c, where c is a constant. From observation, we can see that the gradient of a horizontal line is 0, and therefore the derivative of a constant function is also 0. In other words, derivative of c d dx c equal to 0. You may not be convinced by this, but algebraically, we'll let fx equal to c, which is a constant. By the limit definition of derivative of c equal to f prime x, and f prime x is equal to the limit of delta x approach 0, f x plus delta x minus f of x over delta x. Let's say we bring back this function. We have a y equal to c, which is a constant function. We plot several points on this graph, and we'll still get a c. When we want to find the gradient, it's just c minus c, and c minus c is 0. We can conclude that d dx, or derivative of a constant function, is equal to 0. That is our constant rule. Okay, moving on. The next rule we want to prove is the power rule. Before we prove the rule, we have to review the procedure of expanding a binomial. Let's say we have a x plus delta x square is actually equal to x squared plus 2x delta x plus delta x squared. If we have x plus delta x cubed is actually equal to x cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed. The general binomial expansion for a positive integer n will be xn, x power n plus nx power n minus 1 times delta x plus n bracket n minus 1 times x power n minus 2 over 2 times delta x square plus etc. until delta x power n. This is the general binomial expansion formula. So now, if n is a positive integer greater than 1, then the binomial expansion produces the following. Derivative of x power n is equal to the limit of delta x approach 0 of x plus delta x power n minus xn over delta x. And if we sub in the binomial expansion from earlier, we'll have something like this. I don't want to read it anymore because it's very long. Okay, so you just try to understand it. And remember the minus x power n at the back. Okay, so for now, we'll simplify this. And the xn and xn can cancel each other. Delta x divided by delta x also can cancel each other. Delta x squared divided by delta x, we just minus the power by 1. And same thing goes for the power n, we just have power n minus 1. And this is why we will end up having in this form, nx power n minus 1 plus the fraction times delta x plus blah blah blah, and at the end is delta x power n minus 1. Okay, since we take the limit of delta x approaching 0, delta x, the whole thing here, will be 0. This thing also 0. 0 times any fraction is still 0, and 0 to the n to any power is still 0. Therefore, we will have nx power n minus 1 plus 0 plus 0 plus 0 plus 0 plus 0. Okay, so it's just n power x n minus 1. So this is our power rule, where the derivative of x power n equal to n times of x power n minus 1. Okay, next one, I want to prove the constant multiple rule. Constant multiple rule is usually used when the whole function is multiplied by a constant, which is like this. I want to find the derivative of fx, and fx is the whole function is multiplied by c. So by the definition of derivative that we defined earlier, equal to the limit of delta x approach 0 of c times f of x plus delta x minus c times f of x over delta x. And for the c, because it is a constant, we can factor it out, and we'll have like this, limit of c, and then we bracket the whole thing. And we just take out the c, and it will be equal to c times f prime x And this is the constant multiple rule. Derivative of c f x equal to c f prime x. Informally, the constant multiple rule states that the constant can be factored out of the differentiation process, even if the constant appear in the denominator. So let's say we want to find the derivative of a function fx, which is divided by c. Divided by c is meaning to say that multiply by 1 over c. So we have something like this, where my 1 over c is taken from the bracket. When we take it out, it will be easier for us to solve. So we just have to find the derivative of fx, and we multiply by 1 over c. This constant multiple rule will be very useful to prove other formula and rules. Okay, next we'll move on to the fifth rule, which is the sum and differences rule. Sum and differences rule is used when we want to find the derivative of two functions added together, where both functions are differentiable to x. For example, I want to find the derivative of fx plus gx, where f and g are both functions of x. And then by definition of derivative, we just have to x delta x to every x term for both f and g. So we'll have something like this. Then we'll expand this bracket. We just put a negative inside. We'll have something like this. We expand the bracket. Minus fx minus gx. Then next, we just have to further simplify it by splitting the fraction. So I have limit of delta x approach 0 of the first thing, and limit of delta x approach 0 of the g function. With that, we can differentiate it. For the red color part, we just put f prime x. For the blue color part, we just put g prime x. And this will get the derivative of fx plus gx will be equal to f prime x plus g prime x. So we can say that the sum or sometimes differences of two differentiable functions is differentiable and is the sum or differences of their derivative. And this is our sum and differences rule. Okay, the next rule is the chain rule. So I think I will explain this by using an example question, something like this. Alright, so a set of gears is constructed as shown in the figure, such that the second and the third gears are on the same axle. As the first axle revolves, it will drive the second axle, which in turn drives the third axle. So we let y, u, and x to represent the numbers of revolution per minute of the first, second, and third axle respectively. So we want to find dy over du, du over dx, and dy over dx. And then we have to show that dy over dx is equal to dy over du times du over dx. Okay, this is the source of the question. Alright, to solve this question, because the circumference of gear 2 is 3 times of that of gear 1, so axle 1 must make 3 revolutions to turn axle 2 once. Similarly, axle 2 must make 2 revolutions to turn axle 3 once, so we can write dy over du equal to 3 and du over dx equal to 2. Okay. Alright, so we combine these two results. We'll know that axle 1 must make 6 revolutions to turn axle 3 once. Thus, dy over dx is equal to the rate of change of axle 1 with respect to axle 2 times the rate of change of axle 1 with respect to axle 2. It's the same as dy over du times du over dx. It's 3 times 2, so it's 6. And this 6, the meaning of this 6 is the rate of change of axle 1 with respect to axle 3. Indirectly, we already proven that dy over dx equal to dy over du times du over dx. And this is our chain rule. The concept of chain rule itself is just that the derivative of y equal to fu is the derivative of outer function times the derivative of inner function. For example, we have the y equal to fgx equal to fu, where fgx is actually a composite function. The one in red, which is f, is outer function. The one in blue is inner function. And algebraically, I want to prove whether it is true and whether it makes sense or not. We will just multiply dy over du times du over dx algebraically. So we can see that du and du can cancel out each other. So we have dy over dx on left hand side and dy over dx on right hand side. Therefore, it is algebraically true. With the concept of chain rule, when we combine it with power rule, if y equal to ux power n, where u is the function of x, then dy dx equal to n times of u of x power n minus 1 times du dx, or equivalently, the derivative of u power n equal to n times of u power n minus 1 times u prime. So this is a general power rule. This general power rule is a special case for chain rule, and is very useful when we want to prove other formulas and also for the application of differentiation. Alright, so next rule we want to prove is the product rule. For product rule and quotient rule is actually the two most commonly used rule when we want to differentiate a function. Alright, so product rule is used when we want to find the derivative of a composite function where the first function is multiplied by the second function. We'll let y equal to u times v, where u and v are both differentiable functions to x, meaning u and v both contain x as a variable in the function. So we'll write y equal to uv as equation 1. From first principle, we just add delta y to y and delta u to u, delta v to v. We'll write y plus delta y equal to uv plus u times delta v plus v times delta u plus delta u times delta v as equation 2. We use equation 2 to minus equation 1. We will have delta y equal to u times delta v plus v times delta u plus delta u times delta v. This is our equation 3. We now divide equation 3 by delta x to get a delta y over delta x. So on right hand side, we will have u times delta v over delta x plus v times delta u over delta x plus delta u times delta v over delta x. And now we take the limit on both sides. We will take the limit of delta x approach 0 so that it will fit in our definition for derivative. So you can see we actually use constant multiple rule here for u and v. We just take u and v as constant and we put it out. And for the last term, we just pull out the delta v and put it at the back. So we bring it here. As delta x approach 0, delta v generally also tend to be 0. This is because v is a function of x, mean it contains x. When my delta x is very small and approach 0, we can say that delta v, the change in v, is also very small. Thus, we will write delta v equal to 0, and 0 times with a limit in front, it will be nothing. Now, since we defined earlier, limit of delta x approach 0 of delta y over delta x is dy over dx. Then how about delta u over delta x? It will just be dv dx. And for delta u over delta x, it will just be du dx. Therefore, derivative of uv equal to u times dv over dx plus v times du over dx. And this is our simple product rule. And another way to prove this product rule is like this. This method will involve a clever step where we add and subtract of the same quantity. You see the one in blue, which is f of x plus delta x times gx. In blue, I will add it, and in red, I subtract it. So at the end, it's actually plus 0, it's still the same. However, because of this step, I can split the fraction, and then I will further simplify it later, and at the end of that, I will still get the same product rule. So this is another method, but because the step may appear to be unmotivated to the students, so I would still recommend to prove the simple product rule like earlier. Okay, we are finally here to the last rule, which is the quotient rule. Quotient rule is like the product rule, is used for composite function. But in this case, for quotient rule, we just want to find the derivative of u over v, where u and v are both differentiable functions to x. So we'll write y equal to u over v as equation 1. From the first principle, just like just now, y will plus with a delta y, u will plus with a delta u, and v will plus with a delta v. This is our equation 2. Use equation 2 to minus equation 1. We'll have delta y equal to u plus delta u over v plus delta v minus u over v. And now we just do simple fraction operation where we multiply v times u plus delta u minus u times v plus delta v over the denominator will have the same, which is v times bracket v plus delta v. And now we just expand the fraction. We times the v and u into the bracket. So we have vu plus v times delta u minus uv plus u times delta v over v bracket v plus delta v. We will now write delta y equal to v times delta u minus u times delta v over v times bracket v plus delta v as equation 3. Now we divide equation 3 by delta x because I want to get dy over dx, right? So we will have dy over dx equal to v times delta u over delta v. So we will have v times delta u over delta x minus u times delta v over delta x over v times v plus delta v. Now we'll take limits on both sides, so we have something like this. Since delta x approach 0, so delta v also approach 0 because v is the function of x. Then limit of delta x approach 0 of v plus delta v will be 0 because v plus 0 is still v. We substitute into the equation earlier, so we will have v times v as denominator, which is equal to v squared. Move it here. Since limit of delta x approach 0 of delta y over delta x is dy dx, we'll have dv over dx and du over dx. Therefore, derivative of u over v equal to v times du over dx minus u times dv over dx over v squared. And this is our simple quotient rule. But we have the condition for v. V cannot equal to 0 because if v is 0, then the whole fraction will be undefined, and therefore we conclude that we set the condition that v cannot equal to 0. Same like product rule, we also can prove it using the method earlier, which is we add something and minus out something of the same quantity. So in this case we will add fx times gx and we minus out fx times gx. At the end of the day, we will still get the same quotient rule with different notation. Alright, so this is all for today. What have we covered today? We have come to the first principle of differentiation from the tangent line problem. We have proved that the derivative of a constant function equal to 0. And we have proved the power rule. We also proved the sum and differences rule. We proved constant multiple rule. We also proved chain rule, product rule, and quotient rule. So for part 1 of the video, we have proved 8 of them, and there are still 10 more to go. Today's progress, about 1/3. So for the next video, I will be proving the derivative of trigonometric function. And see you guys in the next video.